Hello, everyone. My name is Daniel Ohm, and I'll be recording these series of lectures on basic quantum information theory for the Fundamentals of Quantum Information study group at the Quantum Information Science Club Association, KISCA, in South Korea. I'm the vice president of SQRT, the Seoul National University Quantum Research Team. And these series of lectures are designed to help newcomers to the field of quantum information science get their toes wet and get started with the field of quantum information. So, to take a look at the syllabus, basically, we start out with the basics of linear algebra, which is the language of quantum mechanics, the fundamentals of quantum mechanics, and then we move on to some of the basic notions of computer science, such as complexity theory and logic gates. We then move on to the basics of quantum circuits, and then we cover some fundamental quantum algorithms, such as the Grover algorithm and the quantum Fourier transform. Afterwards, we're going to look more into some advanced topics such as the BB84 protocol and Bell's inequality. And we finally wrap up the series of lectures with some notes on quantum information theory and some advanced concepts such as the Shannon entropy and density matrices. In addition, we also cover noise and error correction using the Shor code, which will end our series on the basics of quantum information theory. If we have the time, we'll also get into some coding with Qiskit to get users familiar with the implementations of quantum algorithms in Python packages. So let's get right into it. So before one can study quantum information science, one needs to be familiar with the language of quantum mechanics, which is linear algebra. So this lecture will be a primer on the basic notions of linear algebra, starting with matrices. So what is a matrix? Basically, a matrix is a method of storing information. You can define it as a rectangular array or table of numbers of symbols, expressions that are arranged in rows and columns. So this is an example of a basic matrix. This would be considered a 2 by 3 matrix with 2 indicating the rows and 3 indicating the number of columns. Typically, in linear algebra notation, we denote the indices of matrices by the subscripts, with the first number being the row number and the second number being the column number. So for example, in this matrix here, the element A12 would be 9, corresponding to the first row and the second column. So in general, we could write a matrix like this with m rows and n columns, and it'll be considered an m by n matrix. Typically, most matrices you'll encounter are matrices with elements in R, the real numbers or the complex numbers. And we denote such matrices as the following, with M, of course, representing number of rows, and N representing number of columns. So matrices undergo operations called matrix multiplication. They're kind of peculiar when one looks at it, but when we go deeper into the meaning behind matrices, they actually become quite intuitive. So to multiply two matrices, A and B, that are m by n, and n by p, we perform the following operation defined by this formula. Basically, for the first matrix A, we take the first row, and for the second matrix B, we multiply that row by the column. Multiply each element, the first element of the first row, by the first element of the first column. Then we add the second element of the first row by the second element of the first column of B. So it would look like this. And that would be the first element of the new matrix, basically. We then continue this process with the first row and the second column being multiplied for the first row and the element in the first row and the second column, the resultant matrix. So this would be 19. We have 1 times 6, add 2 times 8, which is 24. We have 3 times 5, add 4 times 7, which is 43. And with 3 times 6, add 4 times 8, which is 50. So we would get this. So let's look at example 2. Here we have a 2 by 3 matrix multiplied by a 3 by 1 matrix. So if we have a 2 by 3 matrix, we would get 2 times 2, 2 times 2, add 1 times 3, add 3 times 5. And then for the second element, the first element of the second column, we have 2 times 5, add 0 times 3, add 1 times 5. So this would evaluate to around 18, 19, basically 10, 15 right here. So you'll begin to notice a pattern. When we multiply a n by n matrix with an n by p matrix, these n's basically cancel out, and we get a n by p, m by p matrix, which is because that I repeat myself, for the element in the ith row in the jth column, we multiply the vectors. If just ignore this k for a second, this is the row, the ith row. This is the jth column. We take all the elements in the ith row of A and the jth column of B, and we multiply them and add them together, basically. So now another operation we can do is called the transpose or the conjugate transpose. So basically, the transpose of a matrix is basically an operation that just flips the matrix over its diagonal. So rows become columns. As you can see here, the first rows become the first column, and the second rows become the second column, or columns becomes rows. So the first column here is the first row there. So formally, you can write the transpose of A as A to the T, basically the superscript. And formally, it's defined like this. We just flip the indices between the rows and the columns. Now, there's a few properties you can derive. I won't derive them here, but if you have the time, you can derive them on your own. That if you have a matrix product and you take the transpose of that, it's the same as taking the transpose of the matrix taking the matrix products of the transpose of each of the matrices, but you flip the order basically. And obviously, if you take the transpose of the transpose, you get your original matrix. Now, the conjugate transpose is basically taking the complex conjugate of each of the elements of the transpose. So it doesn't really matter what order you do it in, you get the same result. And we physicists, we like to call this Hermitian transposes. So basically, a Hermitian transpose would be equivalent to taking the complex conjugate of the matrices and then taking the transpose. So something kind of like this. Basically, the first row becomes first column, first row, second row becomes second column, and we take the complex conjugate of each of these elements, but of course they're real numbers, so it doesn't do anything. So in this case, AT is equal to a Hermitian. This Hermitian. But for example, if we look at this matrix here, we have imaginaries. So the conjugates do matter. So first we take this row, take it as second column, and notice we have taken the complex conjugate of this element here instead of the original element. And we do the same over here. So of course, there are a few properties you can derive if you want, but these are basically identical to the original transpose. So let's move on to a special matrix, which is called the identity matrix, which is a square matrix with ones on the main diagonal and zeros elsewhere. And this guy is special because it acts as a identity element for matrices, which in layman's terms means that if you multiply this identity matrix with any matrix, we just get the same matrix. Now, there's a slight caveat to that, is that matrix multiplication is not commutative. Basically, when you do matrix multiplication, the order matters. So if you go back over here, let's say instead I have this matrix D. Let's multiplies these two together. Is this the same? Well, you can try reversing the order on these. Let's see what you get. What you would get is something like this. You basically get, let's say, 5, 5 at 8, 18, 23, 10, 24, 34, 7, 24, 31, 14, 32, 46. So basically, as you can see here, matrix multiplication is not always commutative. That is, the order in which you multiply gives a different outcome. So a slight caveat to that applies to the identity matrix as well. So for example, if you have a matrix element that's m by n, you would have to multiply an m by n identity matrix to get the same m by n matrix, because as I mentioned earlier, these cancel out, and the final dimension is this. If the identity element was on the right side, it would have to be n by n instead to get an m by n matrix. Moving on, we can also define the inverse of a matrix, which basically is the matrix which gives you the identity matrix when multiplied by the original matrix. So it's defined as the matrix B, which satisfies the property that A times B is equal to B times A, is equal to the identity matrix. Now we have to be careful because there's a reason why it's defined by A, B equals BA. The inverse, in fact, is only defined when A is what we call a square matrix. So when M is equal to N, we say that A is a square matrix because, of course, it looks like a square. Same number of rows, same number of columns. Be a square matrix. If these were unequal, it would look like a rectangle. It wouldn't be a square matrix. So the inverse is only defined for square matrices. And when you multiply B times A or A times B, we get the inverse matrix, which would be N by N as well. So we choose to denote this as A to the minus 1 because you can prove, I won't prove it here, but you can prove if you want that B is unique, basically. So if I have a matrix A, there is a corresponding inverse matrix, A to the minus 1, and there's only one such matrix. I cannot have two different inverses which have the same property listed here. It's quite a remarkable result, in my opinion. So there's actually a quick formula for calculating the inverse matrix of any 2 by 2 matrix. I won't prove it here, but it's pretty simple to prove using some multiplication. If you have a matrix A, B, C, D, 2 by 2 matrix, the inverse is defined by this formula. And the slight caveat is that if you see this quantity over here, this quantity needs to be non-zero because of this fraction over here. And this quantity is special in some way. We denote it as what's called the determinant of A for this 2 by 2 matrix. We won't cover determinants in this lecture now, but we may cover it at a later time when it is required. Let's move on to vectors. It's quite awkward because vectors are basically smaller matrices and we're defining them after we've covered matrices. But to give the formal definition, a vector is basically a quantity that has a size and direction. So it's more intuitive to think of them in terms of being the opposite to what's called scalars. Basically, own the pure magnitude. Quantities that do not have a direction. For example, like quantities such as pi or 5 or the number of states in the US. These do not have a defined direction, but they do have a magnitude, do have a size. On the other hand, vectors, they have an additional dimension called direction. For example, if I have a stick on a plane, an arrow on a plane, I have a length, but I can also give it a direction. So even if I had multiple infinite amounts of sticks with the same size, if I rotate their direction, they're clearly the same object, such as in a circle. So in a circle, you have lots of different points which have the same magnitude from a certain point, but they're all in this different direction. So they're clearly not the same. So that's the formal definition of a vector. And we can represent these vectors using columns, basically small matrices, n by n matrices and 1 by n matrices. So n by 1 matrices are column vectors, and 1 by n matrices are what we call row vectors. We also, to distinguish them from scalars, above the variable, we tend to write an overwrite arrow to indicate that these are vectors and have an additional element of direction. Or you can represent them as bold fonts as well. Now, in quantum mechanics, we also have another type of notation, which is called the bracket notation or direct notation, which is basically a fancy way of writing column vectors and row vectors. So for a column vector, you would have these angle brackets pointing to the right, and for row vectors, you would have these pointing to the left. So here you can see these examples that for these column vectors, these are pointing to the right, and these are pointing to the left for row vectors. Now, why do we represent vectors as these series of numbers? Now, let's take, for example, a point on 2D plane. Basically, there are two elements to this direction, one going this way, another going this way. Basically, to fully represent the direction and size of this point, where this point is located relative to the origin, we could denote it as being, for example, 1, 2, 3, 1, 2, 3, let's say steps to the right and 1, 2, 3 steps up north. You would need at least two numbers to represent this point. But as let's say we have a three-dimensional point, you would also have an additional number for the height and so on. So if you had n dimensions, you would need as many as n points. So in theory, in any dimension, you could represent a point in space using these column and row vectors, which is why we use them for representing quantities that have size and direction. So how do we, another operation, an operation you can do on vectors is what's called the inner product. Now the inner product is a fundamental operation in linear algebra. And in the context of geometry, what inner products represent is how close, basically, two vectors are in direction. So this is the intuition behind it. How close are these to direction? Let's say we have two vectors in 2D space, just to be, you know, keep things simple. We know that these stick them together. We would like to know how much they differ in direction, basically. How could we measure such quantity? Well, that's what the inner product aims to do. So let's say A and B are each represented at A1, A2, A3, B1, B2, B3. The formal definition of the inner product is to multiply each of these elements and add them together, which looks very familiar, doesn't it? It's basically the matrix product we saw earlier for these two matrices. And in bracket notation, we can represent them as putting these together. So since this is a row vector, we'll point to the left. Since this is a column vector, we'll point to the right. And we represent the inner product between these two vectors as this. And this is linked to how close these two vectors are in direction. So if this angle theta is pi over 2, we would have an inner product of 0. And if this theta was 0, basically their direction is the same, be at its maximum. Or the size length of A times the length of B. Now, let's say B is equal to A. What would you get? Just get the length squared. So another way of representing the length is, in fact, a square root of the inner product of A with itself, which we will see later on to be the magnitude of A. So let's moving on. There are some more interesting properties and definitions we can define using inner products. The first obvious result is that the inner product is in fact a scalar. It itself is a number. This is just given by definition. Now, two, there's something that's called skew symmetry. We can define something called skew symmetry. Basically, it's we have the inner product of the row column of B is equal to the complex conjugate of the reverse inner product. This may not seem clear at first, but if you look over here, the row vector and column vector, each column vector has a corresponding dual row vector, which is defined like this. The complex transpose of the column vector is a row vector and vice versa. So being this, if we were to take, for example, if we were to take this inner product and we were to instead rewrite it as this, basically like this, find this as the if we were to take the complex conjugate of this, we would get, of course, this. And this is also akin to writing So we just switch A and B. So that basically proves that the complex conjugate of this equals this, which is equivalent to this statement over here. So we like to call this property skew symmetry. Another property we have is of positive semi-definiteness, basically, which states that the magnitude, basically the inner product of A with itself, is always greater or equal to zero. This is obvious given the definition, basically geometric interpretation over here, but it can also be seen from the definition, basically A1 convex conjugate and A2 convex conjugate, and A3 convex conjugate, which is basically the magnitudes squared, the absolute values squared, and summed up. And by definition, these are greater or equal to zero. Another important property is that the inner product is what's called a linear operation, which basically means that if we have, for example, this component right here, which is the linear combination of A and B, basically what that means is that we multiply a scalar by this vector, and we add it to the multiple of another scalar times the other vector. This is what's called a linear combination. And if we were to take the inner product of this linear combination with another vector c, the full result would be basically equivalent to doing the linear combination of c times each of the individual vectors. I like to think of this as commutativeness of the multiplicative and the additive operations. Basically, it doesn't matter if you do the inner product and the sum first, or the sum first times scalars, and then the inner product. This property of linearity shows up multiple times, all the time in linear algebra, hence the name. And it's very useful because if you have a complex quantity, but you know what the complex quantity is a linear product of, you simply take the operations of the vectors that comprise that quantity, and then you just take the linear combinations of that result. What that implies is that if you know something that's called the basis, basically the vectors that comprise a linear combination, you can gather information, extract information on the operations of what the linear combinations of each of them will result in. Okay, so let's do a few examples of inner products, basically. The inner product that we use, as I mentioned over here, is what's called a complex conjugate times this, the column vector over here, which is defined over here. Notice how this differs with the one mentioned earlier, defined by four real vectors. Because in general, of course, most vectors we're going to use are complex in nature. And that is the case in quantum mechanics. And so, for example, let's say we reversed, for example, we had this inner product here. Let's say we reverse the order. So we would have this vector here, basically. The result would be 2 minus I at 3 equals 5 minus I, which is in fact the complex conjugate of that, which is example of skew symmetry. Okay, now let's talk about magnitude. As I mentioned earlier, the magnitude of a vector is basically the length size of the vector. And of course, how to find the magnitude? For example, let's say you have a two-dimensional vector. So we have this length A and B. And let's say this is the imaginary. This is the real or something. No, I mean the X and Y. You use Pythagoras basically. So A squared, just be square root of A squared, B squared. This would be the length. And of course, you can apply this to nth dimensions. So for a vector Cn, we get the length of C is equal to the sum of the squares, square root. And this is the same, as we've seen earlier, as the inner product of C with itself. And we're taking the square root of that. This is also similar to the notion of magnitude of a complex number, where we're just replacing the x and y vectors, x and y axes, with the imaginary real axes. And we have, for example, the real part is x, imaginary point is y. So the magnitude of this complex number, let's say z, of course, would be the square root of x squared and y. So that's how we define magnitudes of complex numbers and vectors. Now, another important notion in linear algebra is what is called eigenvectors and eigenvalues. So basically, eigenvectors and eigenvalues are defined by the following. Let's say we have matrix A. And now an eigenvector is a vector with the property in which that if we perform a matrix multiplication, we basically perform the multiplication between A and the eigenvector called lambda, we would get a scalar multiple of that vector. Intuitively, what this means is that, let's say we have this vector lambda in space, and the matrix multiplication of A on this vector can be seen as this transformation, basically. How would this change? Well, for an eigenvector, it would be simply an extension or a contraction, or a change in direction of the opposite direction. But the vector is still on the same line that's comprising of here. So these vectors are called, they're special, they're called eigenvectors. And the amount that is contracted or extended is called the eigenvalue of A. So for example, let's say we have this matrix over here. We multiply this matrix and we get 1 over I again. So the eigenvalue in this case would be 1. And the eigenvector in this case would be 1i. And then the same could be said for I minus I. So if we multiply it by this vector, we get I minus I times -1. So the eigenvalue would be -1. The eigenvector would be I minus I. So now we've covered what eigenvectors and eigenvalues are. Let's talk about how to actually find them for once. So we take the definition of eigenvectors and eigenvalues. This can be rewritten as the matrix multiplication of the identity with the eigenvector. We're going to move this to the opposite side by subtracting both sides by the quantity. Sorry, my handwriting is terrible. And now we're going to use a property I mentioned earlier called the linear property, basically, which means that we can factor it out like so. So basically, this is possible because this matrix multiplication times this vector is also equal to the matrix multiplication and their sums, the sums of the individual matrix multiplications. And of course, the opposite, the right-hand side would be 0. Now, I mentioned earlier that the inverse of a matrix only exists if the quantity called the determinant is not 0. So if it's not 0, then the inverse of the matrix on the left-hand side exists. So let's say it is not 0, then we can multiply both sides by that inverse to obtain this formula, basically. And of course, these two cancel because of the definition of the inverse. And we yield the eigenvector here, and we get 0. So this is what we call in math a trivial solution. Basically, it's obvious. Duh. Of course, if you multiply by 0 on both sides, we get 0. So we don't want this. We don't want this. We want the cases where the determinant is 0. And we're going to exploit this fact to find basically lambda. So for the simplest case of 2 times 2 matrices, this formula actually yields us a quadratic equation. So let's go over it step by step. First, you write down your matrix, and you write down your lambda times the identity, and we subtract them to get this final matrix. So subtracting involves taking the elements in each indices and subtracting them, basically. So we get 4 minus lambda, 2. 2 times 0 is 2. 2 minus 0 times is 2. 3 minus 0 is 3. 5 minus lambda is this. And then the determinant is calculated for 2 times 2 matrices by 4 minus lambda times 5 minus lambda minus 2 times 3. Basically, this diagonal, the multiplication of this diagonal, multiplication of this diagonal, and just subtract these. So 4 minus lambda times 5 minus lambda, -6, and then you would, let's clean up these terms. To clean up these terms, we would get this expression. And if you remember from middle school algebra, we can factorize this to be this equation, and solving this gives us our eigenvalues. So how do we find the eigenvectors? Well, it's a bit of a cakewalk now that we found our eigenvalues. So if we substitute them back in here, we know that the eigenvector times A minus the eigenvalue times the identity matrix is 0. So if we just set this as our unknown, we can then plug this back into here to obtain this vector. And this will be equal to the 0 vector. So what do we get? We get a system of linear equations. Now, the slight caveat is that it can't be solved exactly. No, what am I saying? It has multiple solutions, in fact. So solving this gives us this general relation x1 equals minus y1, which means that we technically have an infinite number of eigenvector candidates. But normally, the nice thing to do is to just choose the one in which the magnitude of the eigenvector is 1, which is called a normalized vector. Normalized eigenvector. So normalization means basically making the magnitude to 1, making the magnitude 1. So since we have this value, we then find x such that it is 1. So x would be 1 over square root of 2. Of course, a plus minus, you can choose any one you want, but let's just choose the positive one. Then we get 1 equals that. And that's our final eigenvector. So now we've covered how to find eigenvectors and how to find eigenvalues. Let's move on to the final sections, final topics of our lecture. These are the Hermitian and unitary matrices. Now, Hermitian and unitary matrices, as we'll see in the next lecture, are extremely important. They're basically the fundamental matrices of quantum mechanics. They basically are the matrices that represent physical processes and physical quantities. So a Hermitian matrix, for starters, is a matrix which has the same, basically, it's a matrix where the complex conjugate transpose, aka the Hermitian, is equal to itself. Now, why do we care about Hermitian matrices, for starters? Well, they have the following interesting properties. First, the eigenvalues of a Hermitian matrix are real. Second, two eigenvectors of a Hermitian operator with different eigenvalues are orthogonal, which basically, orthogonal basically means that two vectors have a 0 inner product. So what are the consequences of these properties physically, basically? Well, the first one, the eigenvalues of Hermitian matrices are real, means they can represent physical quantities. Second, two eigenvalues of a Hermitian operator, different eigenvalues are orthogonal, which means that the eigenvectors can form a basis, just called basis, which I will cover later on. But basically, a basis is a general axis of basically all the vectors, the space in which all the vectors exist. So for example, for size 2 vectors, basically, so vectors with like A, B, two elements exist on the 2D plane. You only need two axes to represent all of them. So basically, the basis vectors would be 1, 0, or 0, 1. So any vector in 2D space can be represented as the linear combination of these two bases. Of course, these two bases aren't actually unique. You could have like two if you wanted, or even three. But the point is that since these eigenvectors are orthogonal, they're perpendicular to each other, they both all represent different directions. If they were perpendicular to each other, there would be some overlap. Basically, they would share some component of direction. Does that mean that they cannot represent a basis in this case? That's actually not the case. But if they're orthogonal, they're certain to form a basis. So although it doesn't always mean that if you're not orthogonal, you don't form a basis. That's not always true. But it is true that if you are orthogonal and you have a sufficient amount of orthogonal vectors, you are certain to form a basis. And that basis is what's called an orthogonal basis. In addition, if you have a basis formed from eigenvectors, you get what's called an eigenbasis. So finally, let's prove these useful properties. So you have an omega, the Hermitian matrix, and you have the normalized eigenvectors of omega. By definition, of course, you can write this. Now, the trick is for property 1 is that we're going to take the row vector of one of these eigenvectors and plot them over here, take the inner product. So we write it like this. The right-hand side will become this. And of course, we get this. And here, we're assuming that these are normalized. So this would just be 1. So this would be lambda I. Then we take the Hermitian of both sides, which leads us to this, which further leads to this. But since this is Hermitian, we get just omega again, and this simply flips to here, and this simply flips to here, getting what we started out with. But on the right-hand side, obviously, if we take the Hermitian of a 1 by 1 matrix, basically a scalar, we just get the complex conjugate. And the complex conjugate needs to be equal to this because we got what we started with on the left-hand side. So our conclusion is that lambda I is equal to lambda I complex conjugate, which is the definition of a real number. Now for a second property, instead of plopping lambda I on the left, we're going to plop lambda J on the left, which gives us this quantity over here. So basically what happens when you do that is that if you follow the algebra, the trick we're going to use is that omega is Hermitian. So we can rewrite it as this, omega Hermitian, which is the same as this, because this quantity over here is equal to over here, like that. But that is what is the information of the rule. And then if we flip the order and then put a complex conjugate, we get this result. But of course, according to the definition of the eigenvectors, we can rewrite this as this over here with a lambda j for the eigenvalue. And then we finally apply our Hermitian to obtain this quantity over here. Now, this is equal to this. So if we put this over to the left-hand side and factorize, we get this quantity. Now, if lambda I and lambda j are not equal, then we get this result. These needs to be 0. Which means that since we've assumed lambda I and lambda j are different for different i's and j's, basically they're all have different eigenvalues, which means that in fancy jargon, we've assumed they're non-degenerate. Then lambda j and lambda I must be equal to 0. So they form orthogonal vectors. Finally, moving on to the final topic of today's lecture, we have something that's called unitary matrices. So a unitary matrix is basically when we have a Hermitian, a complex, the Hermitian of a matrix being the inverse. So when we have an inverse, which is equal to the Hermitian. Why are these important? Basically, the eigenvalues of a unitary operator are complex numbers of unit modulus. They're basically numbers of the form e to the I theta. So they live on the complex plane with a magnitude of 1. And secondly, the eigenvectors of a unitary operator are mutually orthogonal. Basically, as we saw with the Hermitian matrix, if we have a set of vectors, eigenvectors of a unitary operator, they too form a orthogonal set of matrices. So let's look at the proof. Property 1. Let's say U is our unitary matrix and Ui are our normalized eigenvectors of U. So U multiplied by Ui is, of course, by definition, this form. But let's say we have two different eigenvectors. Then the trick is to take the Hermitian of both sides to get this equation on the right. And then we finally, we then, let's say we apply ui to the right as an inner product. We can then rewrite this as having we slip in an identity matrix, but by the definition of a unitary matrix, we can rewrite this as this. But we know that this is equal to this, and this is equal to this. And so we get this final quantity right here. So we can do some algebra to put this to the left-hand side to get this equation. So when I is equal to j, you get ui is equal to 1, which implies that this expression is 0. If we go down the trail of algebra, we then get the result that the magnitude of ui is equal to 1. In the other case, if I and j are not equal, then this is not equal to 1. So this must be 0, since the products are 0, which means that they are orthogonal with each other. Now, some additional notes. We can sometimes define additional functions by using the definitions of already existing scalar functions. So for e to the x, we know e to the x is defined by the Taylor function over here. Now in linear algebra, we define e to the omega for matrix omega as the Taylor series of the matrix multiplications summed with each other. Another note on notation is something called the Krokener delta. For those unfamiliar, we're going to use this frequently, so that's why I'm talking about it right now. The Krokener delta is this quantity that's defined as 1 when I and j are equal to each other, and 0 when I and j are unequal to each other. So, delta 2 would be equal to 1 in this case, delta AA will be 1 because they're equal to each other. 2 would be 0 and AB will be 0 if A and B are not equal to 0. Why on earth would you use this quantity? Well, these are actually helpful as bookkeeping devices when doing complex operations in linear algebra. So, for example, let's say you had this quantity here. And if you wanted to say they're orthogonal, you could just say it's equal to the Krokener delta. And of course, like I'm assuming these are normalized. So the Krokener delta pops up a lot of times, frequently in physics as useful bookkeeping devices. They also save a lot of space and are efficient for notations because you don't have to write the cases individually each time. So that wraps up the first lecture of our BQIT series. I hope you learned a lot from this lecture, and in the next lecture, I'll be talking about the fundamentals of quantum mechanics.